So today we're going to talk about something that's really important, analysis and the notion of what's called compactness. Okay, so if you think back to the extreme value theorem, we proved this. So it says that if you have f continuous on a closed interval, then f attains its max and its min, right? F attains its max and its min. And what we saw at the time is that if f is continuous on an open interval, then this is not true, right? It doesn't. You might not attain your max, and you might not attain your min. Right? You could have something like this: 0, 1. 0, 1, and your function could look like this, and then it never attains its, it never attains a point where it reaches the max, never hits the min either. Okay, right? Okay. So so you have to think. Okay, welcome to class. Yeah, please hurry up and sit down, please. Okay. So, what's the difference between these two situations? Right? You've got one where you attain your max and min, and one where you don't attain your max and min, right? And if you look at it, it says, well, it seems like is the difference. Like, what did we use? Do you all remember how we showed that this thing was that this happened? Remember how we showed this? Well, anyway, the key point was that of course, the difference is that this one is closed and this one is open, right? But today we're going to see something that's sort of a different way of looking at this. So today, it's sort of like an alternate viewpoint of this, of why this occurs. Alternate viewpoint of why this occurs. Okay. So we introduced a couple of definitions two classes ago, but it seems like people found them a little bit confusing, so we're going to go over them again. If you have a subset, suppose you have some subset of R. Any collection of open sets G alpha such that E is contained in the union of the G alpha is called an open cover. An open cover. Okay, so you have some subset. Mm-hmm. Yes. This was you came to me afterwards and you said, "I do not understand a word."
Yeah, I didn't know that at all.
Right. Okay. But we did mention this. Okay. So you have some set, and then you cover it with a bunch of open sets. That collection of open sets is called an open cover. Okay. So maybe for an exercise, I'm going to give you this interval here. Somebody give me an open cover of 0, 1.
Can I see the definition?
Mm-hmm.
I haven't absorbed it yet.
Okay. So it's any collection of open sets such that the union of the open sets covers that set. Okay.
Could you just have one open set?
Sure. So give me an open set that covers it.
Negative 1 to 2.
Negative 1 to 2. Okay. So you say let B1 be negative 1, negative 2, sorry, negative 1 to 2. Right. Certainly 0, 1 is contained in the union of these sets, right? Right. So So this thing, just the set B1, is an open cover. Okay. Can somebody give me a different open cover? But certainly, that's an open cover. Somebody give me another open cover. Minus 1 to 10. Okay, that would also work. Right? You can take this guy, minus 5, 10. Somebody give me a cover that is more than one set, or maybe more than two sets, or maybe somebody give me a cover that consists of infinitely many open sets. Say. Can you give me a cover? So here's another example, and certainly we could go on like this, making you can take certainly lots of single intervals. We'll cover this. Let's make it a little bit more interesting. Give me a cover that consists of infinitely many sets. Say. Negative n to n. Okay. So say negative 1, 1, negative 2, 2, negative 3, 3, and so on and so forth. Right. That's certainly an open cover. Right. Or you could say, I'm going to take every point in 0, 1. I'm going to take every point in 0, 1. So you could say, I'm going to take every point in 0, 1. And say take the neighborhood of radius 1/10 around it. Okay. So what that would look like is you've got 0, 1, and every point you'd say, I'm going to take the neighborhood of 1/10 radius, neighborhood of 1/10 radius, neighborhood of 1/10 radius. Everybody is covered. Each point in 0, 1 you cover with the neighborhood of 1/10 radius, right? And that's certainly 0, 1 is going to be contained in the union of those neighborhoods, right? Because you've covered every point, so the union is going to cover all points. Okay. You can do the same sort of thing for the open interval 0, 1, right? You could cover it with opens. Okay. Again, we'll play the game. Somebody give me an open cover of this set. Each end. What's an open cover of this set?
Do you know something like?
It's up to you. It's up to you.
Negative 1, 2.
Okay, negative 1, 2. Or you could even be more sort of, you could even be more sassy about it, right? And just say, well, 0, 1 itself, right? 0, 1 itself, that's an open cover, right? Is an open cover, right? Of 0, 1, because the set itself is open, right? That's an open cover. Okay. Does anyone remember the cover that we constructed on whatever day it was? We constructed an infinite cover that was a little bit tricky. 1 over n, yeah. So it was 0, 1 over n, where right, 0 to 1 over n, where n. Well, actually, I wanted n to be 2 and above. Is that right? No, that's not right. It was the other way around. Okay, so this would work. So certainly, so this is certainly an open cover, right? The one that consists of 0, 1, 0, 1/2, 0, 1, 1/3, and so on, right? I think what we had on Friday, or whatever day it was, I think it was Friday, was this one, 1 over n comma 1, where n is in and from 2 onwards. Right? Right. Do you all see that that's also an open cover? Okay, right, we've got 0, 0, 1 here. Your first set is 1/2 to 1, the open interval 1/2 to 1. The second guy is 1/3 to 1, third guy is 1/4 to 1, and so on and so forth, right? And you see that the union of all these things, that 0, 1, is contained in the union of all these intervals, and from 2 to infinity. Okay, so this is an open cover. Okay. Everyone all right? Okay. 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 So here's the definition. Here's the key definition. What's compactness? Okay. Let K be some subset. Let K be some set. If K has the property that every open cover contains a finite subcollection that is still an open cover. Every open cover of K contains a finite subcollection that's still an open cover of K. Then we say K is compact. K is compact. Okay. Every open cover contains a finite subcollection that's still an open cover. Okay. People abbreviate this usually as every open cover contains a finite subcover. But what they mean is that there's some subcollection of that open cover that's still going to be an open cover. Okay. So let's look at these examples. Okay, so here's the first open cover we constructed. Does it have a finite subcover?
What do we mean by that?
So finite meaning consisting of only finite elements.
The interval itself.
Right. So you just say, well, look, this thing already is a finite cover, so this open cover does contain a finite subcover, namely the subcover consisting of this one thing.
Sorry, how come it's a finite cover?
Because it consists of one element. Finite meaning the number of elements in the cover. Okay, so you have this cover. You have this cover, right? It's got one set in it. Okay. So you say, okay, well, for my finite subcover, I'm going to choose exactly the same thing. That thing has only one element. It's a finite subcover. Okay, so this open cover has a finite subcover.
So how do you count an element here? It's just the integer?
You just count the what?
The number of elements.
It's just the number of elements in the set.
Which is?
I'm sorry, the number of elements in this set here, which is 1. There's only one, so what I think what's getting here is the cover is the collection of sets. Okay. The cover is the collection of sets. So this cover here, the first cover we constructed is this one. It's the set containing the interval -1, 2. Okay. How many elements are in the set? 1. Okay. So this is our open cover, and then you take you say, well, I'm going to take this. I'm going to take exactly that same thing as my finite subcover, because it's finite. It has only one element, right? Okay. Now this one was actually an infinite collection, right? This is an open cover. It's an infinite collection.
It's not.
Well. So the question is, can you find a finite sub-collection that still covers the set?
Yeah.
Sure. What do you choose?
Just choose some.
You could choose this one, say, right? Or you could choose 2 of them or 3 of them. Just choose some. So you say, okay, look, here's my open cover. It has a finite subcover, namely negative 1, 1. Right? Negative 1, 1. Oh wait, that doesn't work. Negative 1, 1, negative 2, 2. Okay? Or I could have just chosen negative 2, 2. Right? So it has there's a finite subcollection of these sets that still covers the original set. Okay? Is that clear, John?
Yeah.
What are you looking for? Are you ready?
There's like a cockroach.
A cockroach? A bird! Oh, it's a bird. Wow. Oh no. Oh no. Oh no, it's hurt. Oh my god. What do we do? Can we?
I don't think we can. John is not going to be too long, right?
Oh no. It did hurt. Yeah, I think it hurt itself on the window just now. Don't get close. Don't get close. I'll tell somebody I'll call somebody to come and get it.
At least the staff isn't holidays.
Oh no, there should still be stuff. It's okay. Oh. Okay.
You just go to concussion.
Yeah, I just crashed into the window. Yeah. Okay. Okay, we'll see what we can do. Right now, let's leave it alone. Okay. 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 So, right. Here we have an open cover. There's a finite subcollection of this open cover that still covers the set. Right. So that's still an open cover. Right. So it has a finite subcover. Okay. What about this one? Does this have a finite subcover? Does this have a finite subcover? Can you choose?
Oh, which one?
So the radius is 1/10. Right? Can you find a finite? Remember how we constructed this, right? Every point has an interval or radius 1/10 around it. Okay. Can you find a finite subcover that still covers the set? Found it?
You can choose 11 of them.
Choose 11 of them, yeah. So just choose 11 evenly spaced points. Certainly, those guys, the union of those sets is going to cover the union of the intervals of radius 1/10 around those guys is going to cover the whole set. Okay? Yeah, or actually, you could choose 6 of them, right? Because the width of the interval is 1/5. Okay. Okay. So this one has right. So you could take 1 6 2 6 1 6 2 6. So take and 1 10 1 6. So I have 6. Where I goes from 1 2 3 4 5 6. Right. So you divide the interval into 6 parts. Right. 1 2 3. Right. 1 2 3 4 5 6. You cover each of them with something of radius. Wait a second. Well, you know. Sorry, let me see, move these guys all over 1/12, right? Sorry. So, 1I over 6 minus 1/12. And, okay, then that'll do it. And then you see that those guys will cover the whole thing. Okay. Okay. Now let's go over here, and what you see. Okay. Right. So does this thing have an open subcover? A finite subcover? Sure. It's finite to begin with, so you just take it. Right. Does this thing have a finite subcover? Sure. What do you take? You just take the first one, right? 0, 1. Right. Just take the first one. 0, 1 is a cover consisting of one element, right? A subcollection consisting of one element that still covers the set. Okay. Now what about this one? Does this one have a finite subcover? The answer is no. Right? There's no finite subcollection of this that's still going to cover the set.
If you want to cover it, then it has to go to infinity.
That's right.
Over it becomes 0, but that is not.
That's right. Then you wouldn't that wouldn't be a finite subcover. Okay. Okay. And so what you see here is that 0, 1 has open covers. Has an open cover that has no finite subcover. So it's not compact. Okay, it's not compact. Okay. Okay. Now over here, have we shown that this thing is compact? To show that something's compact, what do you have to do? You have to show that for every open cover, there exists a finite subcover. Okay. So we haven't shown yet that this thing is compact. We've only shown that we in our limited attempts, have not been able to come up with an open cover that does not have a finite subcover. Okay. Right. It's easier to show something's not compact than to show something is compact. Right? To show it's not compact, you just have to find something that fails. To show something that is compact, well, you have to show that every open cover has a finite subcover. Right? That's hard, right? Because you'd have to do it for all possibilities, right? Or show that it happens for all possibilities. Okay. Okay. Later on, we'll see that in R, being compact is equivalent to being closed and bounded. Okay. So we'll get a theorem that allows us to make it more concrete what it means to be compact. But for right now, we're just going to stick with this definition. Compact means this: every open cover has a finite subcover. Okay, so don't try and use the theorem yet. Okay, so I hope you have some sense now of what it means, what the definition of compact means. It means that no matter what open cover you choose, it has a finite subcover. Okay, so I'm going to talk about some properties of compact sets. Okay, so the first one is this. If K is compact, then K is closed. compact actually forces U to be closed. So what we're going to show, we'll show that the complement is open, right? Because that's our definition of closed, right? That the complement is open. So remember what open means that given any point in the set, there exists a radius so that the open interval around P is contained in your set, right? That your point is interior, right? Every point is interior to the set. Okay. So here's the picture. I'm going to draw it in 2 dimensions. Really, these results hold in all dimensions. I tend to think of them in 2 dimensions. You have your set, but if you want, you can just think of this as an interval. Okay. You have as some subset of the real line. Okay. Anyway, so you have your set here, and this set is compact, and you have some point on the outside. And you're hoping to show that you can find a neighborhood of that P that is contained entirely in the complement. Okay. Okay. So here's how you do it. So pick any P. Pick any P in the complement. Then, for each Q in the original set, so take a Q in your original set, cover it with the neighborhood of radius distance Q minus P over 2. So, here's the picture. You draw a line from Q to P. You take half of that length, and you take an open neighborhood of Q, right? Cover Q with open neighborhood that has half the radius, half the length. Okay. So notice that the same guy around P does not intersect the interval, the neighborhood around Q. Right? If I take the same radius around here, these guys don't intersect each other. Okay. Now, this gives an open cover of K. Right? You cover each point Q with each point Q and K with these things, right? So take a collection of all these things, all these. Right? Cover every point Q with such a neighborhood. Right? Cover every point in K with such a neighborhood. Okay. You do this for you make one of these neighborhoods for every point in K. Certainly, the union of those things is going to cover all of K because you've covered each point in K. Okay. Everyone all right? Everyone all right to this point? John? Yeah.
Would that give an area that looks something like, I don't know, a rectangle with an edge is like not that sharp?
Yeah, well, I'm not really sure to be honest, because over here you're going to have these. So, and then over here your balls are going to be smaller, right? Right. So it's going to be something like it's going to be sort of bulbous, right?
Why does your size of the ball change?
Because the radius of the ball is half the distance to P.
And P is fixed?
P is fixed.
Oh.
Yeah. So you fix this point P. Remember, we're trying to show this point P is interior. Okay. We've chosen this point. We want to show it's interior. Okay. Okay. So now we use compactness, right? We've got our open cover. We're going to use compactness. Take the finite subcover. K is compact. So there exists a finite subcover. Let's say n q I, where I goes from okay, so delta q I minus q over 2. Okay, for some q1 qn and k. Right. So there's some finite number of points in here, and their neighborhoods cover the whole set. So here's P. You know, maybe there's I don't know, four points that'll do. This one, and maybe just 3 points. You notice that there's some finite subcollection here whose neighborhoods cover the whole set. Okay. Because of compactness, you're guaranteed this to happen. Okay. Compactness, right? You've covered the set with all these intervals, all these balls, right? And compactness says that there's a finite number of balls that will still cover the set, right? You've got an open cover. Compactness guarantees you a finite subcover.
Because like the subcovers you take will be open. Still an open cover. Okay.
Yes, that's right. So remember, so what does compactness mean? That given any open cover, there's a finite subcollection of that cover that still covers the set. There's a finite subcollection that's still an open cover. Okay, here it is. You know, these 3 points, say, these three. Right, we covered the thing with balls. There's a finite number of balls that actually still covers the set. Okay, but then you look and you say, okay, now we can construct we can show that P is interior, right? Because there's only 3 sets here, and you say, well, look, let R be the minimum of these 3 radii, right? Of qi minus p over 2, where I goes from 1 and right? Take the smallest radius, right? Take the smallest radius. Here it seems to be this one. Take the smallest radius. Take the smallest radius. Okay. Then the neighborhood with that radius around P does not intersect any of that finite subcover, any elements of that finite subcover. Right? so does not intersect K, right? Because that finite subcover covered K. So what does that mean? That means that that point is interior, right? Because you found a neighborhood around P that's right. Right. What we're saying is that so right, that neighborhood of P is contained in K complement, right? And so that point is that P is interior to K complement. Remember what we wanted to show, that K complement was open, that every point was interior. Right. Thus K complement is open. Okay, so K is closed. So compact implies closed. Okay. Yeah, John.
Would that be another way to prove directly?
Would say it again?
Being compact means just directly show that it's closed instead of using the flipping parameter.
Is there some way to do it directly?
Yeah.
This is sort of the right way to do it, in the sense that right, compactness is you want to use the the definition of compactness, right? That you've got every open cover has a finite subcover. Yeah. So and also this isn't really much of a flip. This is actually the definition of closed, right? To show that the complement is open. So I don't think. I mean, there are other ways of defining closed. And maybe you can get a proof. I think you can probably get a proof by using that other definition. But we don't have that other definition at this point. Okay. Okay. Next theorem. Okay. So suppose we have a compact set K, compact set R, and F, a subset of K. If F is closed, then F is itself compact. Okay. So picture you have a compact set, and you have this set sitting inside of that compact set. Okay. And that set is closed. It turns out that that set itself will be compact. So any closed subset of a compact set is going to be compact. Okay. So any, right, says any closed subset of a compact set is itself compact. Okay. So what do we want to show? We want to show that the set is compact, right? So we want to show, given any open cover of F, right? So you have somebody gives you an open cover of F, right? You want to show, given any open cover, there exists a finite subcover of F. There exists a finite, you want to show that there exists some finite collection, finite subcollection that still covers F. So somebody gives you a cover of F. Right? Somebody gives you some cover of F, and you want to show that there's a finite subcover still of F. Okay? You know that F is contained in a compact set. So the idea is this. You say, well, I'm going to make a cover of the compact set. Okay. I'm going to make a cover of the compact set by throwing in F complement. Right? If I throw in F complement, right? F is closed, so F complement is open. Right? So if I throw in F complement, I'm going to get a cover of that compact set.
Yeah.
Okay. So, and then since the set is compact, there's like a finite cover that covers K. Take out F complement, and you got a finite cover that covers F. Right?
Yeah.
Okay. So that's exactly the proof right there. Right. This covers F. So this union F complement covers K. Okay. K is compact, so there exists a finite subcover. Right, covering K, and then eliminate a complement from that collection to obtain a finite subcover of F. So that's basically what we just said. Okay, so that's an easy argument. Right? Any closed subset of a compact set still going to be compact. Okay. I was going to do something else, but why don't I do this one? This one I can probably squeeze in without confusing you. Okay. So the choice is to do the one that I was gonna do, which I think you might be confused by. You might sort of like blow your minds before you go to Thanksgiving, or to do one that's sort of easier. Okay, I'm going to do the easier one. Okay, so here we go. Suppose you have a continuous function, f is a continuous function from R to R. Okay, and K is compact. Then f of K K is itself compact. And the image of F on K is going to be compact too. Okay. So you have, F is going from here to here. You have some compact set, and you want to see that the image of that compact set is still compact. Right? So here's K is F of K. The image of a compact set still compact. Okay. Okay. So, right, what do we need to show? Right? We need to show. We want to show that given any open cover of the image. So suppose you have some open cover of the image that there exists a finite subcover. Right? Anyone see how to do it? Somebody gives you a bunch of open sets. That covers the image. And says, is there a finite subcollection of that still covers the image? Anyone see how to do it? I'll give you 2 points on the final if you can see.
We have to use the finite case compact, and that there is a finite collection of Taylor's K.
Okay, so you want to use the compactness of K. How do we get an open cover of K?
Well, we look at the epsilon neighborhood that is mapped from each delta neighborhood, since F is continuous within each of those subcovers.
You're very close. You're very close. You could, well, that's not going to get it, but you're very close. F is continuous, right? So what can we say about F?
If, if we go back to the definition of continuity, it's an epsilon neighborhood, and then that implies that the f of x is between in the inside neighborhood of delta neighborhood and f.
Okay, so certainly, I think both you and you're saying something similar to what Raleigh was saying, that certainly for every point here, right, its image is going to lie in one of these sets, right? And so you know that there's going to be a delta ball around here that gets mapped into that. And you could cover K with all those delta balls, okay, and say, well, there's going to be some finite collection of those delta balls that covers K, right? And so you know that, that'll do it, right? There's going to be some finite collection of those delta balls that covers K, and so take the corresponding guys over here, and that will cover F of K. That'll do it. I'll give you the 2 points. Yes?
But let's say a delta ball covers, just two-dimensionally speaking, maybe 20% of the K.
Yeah.
Does that mean the epsilon ball also covers the 20%?
No.
Or then how do we know that if all a finite set of delta balls covers all the K, how do we know that it also covers, that also covers, epsilon ball covers all the F of K?
Well, if you get every point here, then the set over here contains all the images of this.
It's
right?
right?
It will contain all the points, all the outputs for this group. And so if you've got the whole set, well then you're going to get the whole set over here. No matter whether this one goes to 20% or to 5%, you're going to get 100. You've gotten 100% here, right? So you're going to get 100% of everything.
Now you've covered all the domain.
Yeah, you've covered the whole domain exactly. Okay, so that's good. Let me make it a little bit clearer by using the topological definition of continuity. You say, well, look, we know that F is continuous, so F, the pre-image, of each GA is open. Yeah. Okay. So just take each of these guys and pull it backwards through K. Right? That gives us, right, F inverse G1, F inverse G2, blah, blah, blah. That gives us an open cover of K. Right? Then the collection, the union of those guys, right, is an open cover of K. Right? K is compact, so it exists a finite subcover. Finite subcover, F inverse G A I, where I ranges from 1 to n. Right. Finite subcover of K. But then GA1 to GAN covers F. Okay, and so the cover has a finite subcover. Okay, that's basically it for today.